Hey, Andrew McLaren here. We're going to be going over ideal gas laws as well as real gas laws and how they're slightly different. We're going to be focusing more on the concept of the gas laws and thinking about the ideal gas law equation and how it relates to all the different types of situations you might see with these problems. And we're going to do that by looking at like the concept, drawing some stuff out, and then relating that in some simulations to the math. So we'll actually do some calculations and think about how that's related to what we're modeling out. And then we'll work through just like the real gas formula and do a number of practice problems. And by the going through all that, you should understand what this formula is representing and be able to understand like models that relate to it, and you should be able to solve these problems and describe what's going on. Okay. Most problems with ideal gas laws, they tend to fall under one of two categories. It's either you're looking at the same thing with two different times, or you're looking at one thing in one time and you're relating all the variables about it at that one time. So you can see oftentimes they'll do something where it's like this one pressure times this other volume is equal to a second pressure times a second volume. So these subscripts, those typically are referring to like time one and time two, just to help you keep track of what goes where. And then you can see other things like this where you've got pressure times volume is equal to the number of moles times R times T. And then in this case, these are all the same time. And this would be pressure. And then we've got volume. And then this is the number of moles. I just think of this as how much stuff we have. And then this right here is the temperature. And you really are equating those four things, but there is also this constant. So this is just a conversion factor that allows us to convert between our measurements of pressure, volume, moles, and temperature. If you went to a different planet and they use different units, they would have to use a different R value. Like it's still the same stuff that's being relayed, pressure, volume, moles, and temperature. But if we were measuring something instead of with volume being liters, if you had a bigger unit of volume, you're going to need a bigger R value for some number of moles or temperature. So that R is, yeah, it's included in these sorts of problems, but it's more just to convert between things. So it's really one of those two types. And so when I'm thinking about going through my problem solving flowchart, basically what you need to do is be able to do some algebra with these equations. And you also need to be able to recognize what units are important because oftentimes they give you the wrong types of units. And you have to be able to recognize what units are going with what variable, like what is the unit of pressure. And so you can figure out where that number goes, right? So you're going to need to be able to know what units are going where, be able to organize stuff. Drawing pictures isn't like necessary for the calculation on these, but it helps you kind of understand the situation, and then it helps you double check your answer. So that's kind of nice. And yeah, I think that should give us a good start to get us going on problems like this. Also, something, just be very, very careful. They love to give you the units for temperature. They love to give you that in Celsius because we think in terms of Celsius. But if you think about all of these values, it's just plug in like 1 in for each one of these things just for a second. So it's 1 times 1 is equal to 1 times 1 times 1. If you double the temperature here, you would expect to get maybe twice as much volume if everything else is held constant. But you haven't really doubled the temperature when you're gone from 50 or 25 Celsius to 50 Celsius because it's a very small change in terms of actual temperature. In terms of Kelvin, it's like, what is that, around like 300 Kelvin going to 325 Kelvin. It's like a very small change in temperature. So yeah, it's increased in temperature, but not by 50% like you would maybe think here. It's only gone up by like maybe 10 or like 15%. So you have to be careful about your units. Also, grams, you need to turn those into moles to work with these types of problems because you're relating it through the moles here. So just be careful because they like to give you things in grams when you're doing these types of problems. They might do some other weird units for volume, but typically that's in liters and pressures, typically in atmosphere, or they might give you different ones, and then you have to be careful with that. So like on the AP test, this is all you get. They don't give you like the P1, V1, and all that stuff, but you can derive those. And I'll show you that in just a minute, what I mean by deriving that in the concept review. And you'll see problems that typically are like this, where they're like, oh, here's like this pressure, or here's this volume. What do you need to solve for given that you have this new volume? Or maybe they're telling you, like, here's this number of moles, and here's some temperature, and here's some pressure. Like, they're not even telling you that this is pressure, they're just kind of assuming that you know that. So you need to look for that and identify these things, and identifying what are they asking you for. In this case, they're asking you for the volume, and it looks like it's all in one time. So this is like a PV equals nRT, and this is one of those derived things where you've got like time 1 and time 2, and you got to figure out the volume if you have the other volume and the other pressure. So just be aware that that's typically what these problems look like, and that's how you start them. So you've probably seen these various equations where they have like the P1, V1 is equal to P2, V2, talking about like, oh, this of course is equal to that. Or maybe you've got your pressure over your temperature equations, right? So you've got all these different equations relating different pressures and temperatures. And sometimes chemistry teachers will save this for the very end, but I think it's good to just kind of start with this. We're really equating everything through the same equation right here. All of these different things are just essentially the same formula. It's just been rewritten slightly different. And you can kind of see how they're very, very, very similar. But basically what we're doing with all these different relationships is like, we know with a gas, just kind of intuitively, if I make the pressure go down, the volume's gonna go up, right? And so like essentially I'm saying like, okay, if I can maybe make the pressure go up, the volume goes down. So if I squeeze on a balloon, if I make the pressure increase, it's getting like more pressure inside that balloon. The balloon's getting smaller. So we kind of know how these things all relate individually. And you can also say like, okay, maybe I'm increasing the temperature. That's also probably going to increase the pressure. So if you get a gas really hot, maybe that's going to make it increase the size if it's in a flexible container. If it's not in a flexible container, like, so maybe if it's getting hot, it might also increase its volume, or it might also get to higher pressure. So you might get something that's like really hot and high pressure, or you might get something that's very hot and a big volume, kind of depending on if the container is flexible or not. So all of these things are essentially being related through what you know and what you don't know to be constant. So if you look at like this P1, V1, you're basically saying all of this is going to be held constant. And then if I know like this change, I can tell you what that change will be. That's essentially what we're doing. We're saying like, okay, if this changes, how's that going to change and keep everything else constant? And you could rearrange this, and you could have like the PV equals nRT, and you can rearrange this so that you've got T on one side if you divide both sides by T, and then you've got nR over V. And so if in this case, if you're saying, okay, actually I'm going to keep all of these guys to be constant, then as my pressure increases, or sorry, I've just to, if this is being held constant, then if this increases, that also is going to have to increase. So you're basically saying, like, I still have the same number of moles, I still have the same constant, I still have the same volume, but maybe it's a slightly different situation here. So this is kind of like your first pressure, first temperature, and this is now a different pressure and a different temperature. It's still the same number of moles, it's still the same size of the container, it's still the same constant. So this is like if the volume is constant. And then if you think about this, this is saying like, oh, maybe volume can change and then pressure is constant. So in a sense, this is just this equation that's been written in a slightly different way. So now we've got V over T is equal to NR over P. And so now pressure is being held constant and you've got the same amount of stuff, and R is always a constant value. So you've got your V1 and T1, which is equal to a second volume and a second temperature. So really what we're doing with any of these problems is you're saying, because I know how this one thing is changing, I know how this other thing is going to change, because everything else is being held constant. That's kind of how all this stuff kind of conceptually connects. And then you can think about, well, if I know everything in one instance besides one variable, like I was just kind of talking a lot about like the changes going on here. But if you're saying like PV equals nRT, if you know, like, you're like, okay, I know all of this stuff and R is always a constant, then you should be able to solve for the one thing that you don't know. That's always the case. And so these problems are either going to give you everything besides one variable, or it's two different time periods that you've got to make a comparison about two things. So that's kind of what these problems are trying to get you to do. It's either one time and everything is known, or it's like the two times and comparing two variables like pressure or temperature or volume or moles, because they do change the number of moles on these problems as well. So you have to be kind of careful about that. And like I said earlier in the segment before, make sure your temperature's in Kelvin, because all of this stuff is assuming that zero is actually zero. If you think about like this equation, like the PV equals nRT, sorry, that's a weird looking R. What we're saying is basically like this gas is going to not really be giving off very much pressure at low temperatures. Like low temperatures is low pressure. But to do that, you have to have zero actually be zero. Because like Kelvin, remember, if we're talking about like 0 degrees Celsius, that's 273 degrees Kelvin, right? And then if we're talking about like 100 degrees Celsius, that's I believe like that. And so like a lot of people will think like, oh, there isn't very much pressure at 0 degrees Celsius because it's zero, but it's actually got quite a bit of temperature there. So there's going to be a significant amount of pressure underneath most conditions. So you have to be kind of careful. And you can imagine if you plug in the wrong numbers here, you're going to get the wrong calculations. So just be super careful about that. Most of the time, like if you're talking about like this, it's not like it's a little bit different if the units are wrong with pressure or volume, but like zero is still zero. Like 0 liters is still like 0 gallons, or like 0 atmospheres is still 0 bar or 0 torr. So just be a little bit careful about that stuff. And then also one other thing to keep in mind is that R values can be slightly different because as you can see here, this is 8.31 joules per mole Kelvin right here. That's what those negative ones mean, is that those are in the denominator of this fraction. So this we're going to be using with, of course, Kelvin, moles, and joules. But then here you can see we've got our liter atmospheres and our liter torrs. And so you have to use the right one for if you're using atmospheres or torrs. And this is with joules, so you're using this with stuff where you're actually using joules instead of liters and atmospheres. You typically are going to be working with this one. That's usually what I see. And then you sometimes see this one being used. So just be a little bit careful when you're using those R values, because you gotta cancel units. So if you're working, what I mean by this is like if you have atmosphere, and then let's say this is 1 liter for volume. I'm just gonna plug in some numbers here, and let's say this is 1 mole of whatever gas that we're talking about. Then I don't know what this number is. I'm just gonna put this and say that this is 100 degrees Kelvin. It's not really. But let's just say that that's what it is. Just give us a placeholder for the units. So here we need to have some units that would be atmosphere liters over mole Kelvin, because you need to cancel out these moles and you need to cancel out these kelvins and leave you with atmosphere liters. So we need the unit, the R value that's in that atmosphere liters. So it's the 0.0826. Was it 206? So just be careful about that in setting up your R values, right? So let's do some drawn models to understand what we're looking at in the two problems. We can call this problem number 1, and this is problem number 2. So in problem number 1, it looks like we have some pressure and some volume. They want to know the pressure if we have a different volume. So we're relating pressures and volumes. And it looks like there's this relationship when we look at pressures and volumes, that if we were to change this volume, it looks like there's an increase in the volume here, the pressure should decrease, because remember the volume is the how much space there is, and the pressure, this is collisions with side or with walls of the container. So you can imagine that if there's more space, these particles, if they're traveling the same speed and everything, they're at the same temperature, they're going to be colliding with the wall, in this case, less often. So the pressure should go down. So conceptually, that's kind of what's going on with this first problem. When we're looking at this, we know that the volume has increased, so the pressure should have decreased. So that's kind of what's going on there. This second one, how I like to think about these is that we basically have this relationship PV equals nRT. And in this second problem, we have, it looks like the moles, the temperature, the pressure. We don't know the volume. So in this, what we're basically saying is like, let's say that you know all of this information, and that is what we're trying to solve. So in a sense, we know the number, the amount of stuff or the amount of moles of this. We also know their speed. So we know how fast these things are going. We know how many of them there are. And we also know the number of collisions that they have with the side. Um, so let's just put that right here. This is that number of collisions with the wall. So in a sense, you could imagine if you have all of that known, you can figure out how big the container is. Because if you know how many collisions there are, you know what speed they're going at, and you know the number of these things, you should be able to figure out the volume that you get from that. So, yeah, it's kind of like, okay, let's figure out, you know, what the pressure is of a certain temperature and moles. If you double up the moles, it should double up that pressure, right? Same sort of thing. It's all this stuff is related. So we should be able to figure out how much space this is taking up if we know the amount of stuff, its speed, and the number of collisions that are going on there. I did also want to show you a number of bar graphs. And so if you look here, I want to show the relationship between pressure and volume. As you can see, as pressure goes up, volume goes down. And so this is showing that they have this was an inverse relationship. And so you've got like your pressure 1, volume 1, your pressure 2, and volume 2. And these are being related when you have a constant number of moles and temperature. And so you can see that relationship and how those things are related there. And then you can also see if you were to hold the temperature and volume constant here, that pressure and moles, they have a direct relationship. If you double the amount of moles, you double the pressure. So if you've got like 2N, you're going to have 2P, as long as temperature and volume are the same. So you can relate these two kind of like that. And same thing here. Temperature, if you've got twice as much temperature and everything else is constant, you should have twice as much pressure. So this is the main reason that we have to be careful about Kelvin, is that, well, if you are doubling temperature, you should double pressure. So we have to work with the temperature that's actually like zeroed it to reality. And that's Kelvin, because we have found that Kelvin does line up perfectly when we use it in this formula. And so we can also see that if you were to increase number of moles and you had a constant pressure, the volume's going to be increasing. So this container should be getting bigger. If you've got more, like if you have a balloon and you add more moles to it, more stuff to it, it should get bigger because it's a flexible container. And then same thing here, you can see with volume and temperature, how they're related. They're also going to be increasing directly. So if you were to increase, if you had a balloon and you were to make it warmer, it's going to get bigger, right? That kind of makes sense. So if you double the temperature, you should double that volume. This is kind of weird for me to think about this because you're typically not going to change the amount of moles to change the temperature. But you could think about this where you have like the pressure and the volume being constant, and you want to maybe cool something down by removing the amount of moles there are. So you could try doing something like that. It's kind of weird to think about this, but if you were to think about this, if you were to have less moles, wait, yeah, this is a bizarre one to even really think about. But if you were to try and hold the pressure and volume constant, you would have to like if you were to increase the temperature, you would have to have less moles, which kind of makes sense. If you want to keep the same amount of collisions with the outside, if things are traveling faster, you want less of them, in a sense. So that's another way to kind of draw out or see these things visually. Now it's time for the Sims. A really nice way of visualizing all of this information is with some simulations. So if you're getting kind of lost in that last section with me talking about a bunch of stuff, I would really recommend you check out the PhET simulation called gas properties. It's really cool. I'll have it linked on here. So you can like hold the volume constant, and you can then let the simulation run, and you can like increase the temperature and see how that increases the pressure, right? So we're in this case we're holding things constant. So this is that situation where you're changing it temperature, which causes a pressure change. So you can see as one goes up, the other one goes up, as one goes down, the other one goes down, right? So if we were trying to simulate some other situations, they've got, so you can hold the temperature constant. So you're like, okay, well, the temperature is going to be held constant. Um, and so now if I change the volume, that's going to change the pressure. So it looks like I've got like moles are still the same amount of stuff. Um, and so if I hold the temperature constant, if I change the volume, it should change that pressure. So you can kind of see how this stuff all relates and kind of play around with it a little bit. You can also let off some of the gas to let some of it escape. And there's another, you can add in some more of the gas. It's a pretty interesting little simulator that they've got here. But what they're basically showing you here is like all of our relationships. Like you can see pressure and temperature changes and how they relate to each other through this. And so we can go through all of the stuff that we were looking at. Let's just look at our example problem. Let's say that you had some pressure and some volume, and then you increase the volume a lot. Okay, so let's say that we're changing pressure, volume. So let's keep temperature constant, and we're going to start with a very small volume. Let's say that we're starting as small as we can make that volume, right? And then we look at the pressure, that's around 40. And then if we increase the volume, that volume dropped, or the pressure dropped. So increase in volume, decrease the pressure. So it's decreasing the number of collisions that have happened there. So you should know, like without doing any work, you should be like, the answer should be less than 1 atmosphere. Because if this number's gone up, that like the volume's gone up, the pressure should have gone down. So just use a little bit of estimation there. It just is going to save you a lot of pain, a lot, if you're able to do basic estimation with these problems. So that's one way to think about it. Then also, if we're looking at this situation, this is basically saying, okay, you know the number of particles exactly. You know the pressure, you know the temperature, and I want to know the volume. So we should be able to solve for the volume, whatever that size is. So it's just a matter of relating all these different things. As you can see, all of them relate to each other. And so if you understand the temperature, the pressure, the amount of stuff, then you should be able to tell me how much volume there is. That's kind of what's going on with, if you're thinking about that in terms of the simulation. Very, very neat. I would definitely recommend you play around with that just to kind of see how this stuff works. Okay, the moment you've been waiting for, or maybe skipped ahead to, I don't know. So if we look at this first problem, as I said earlier, we can see that the volume's gone up, so the pressure should have gone down. And you can do a little bit of estimation here. This has actually gone up by about 100 times, so this should go down by about 100-fold. So just keep that in mind. These things are directly or indirectly related, so you can use some estimation to help save a lot of time on these things. Okay, so let's say that we have our pressure times volume and our pressure times volume. The derived or shorter formula right here is what we're going to be using, and you could solve for the like pressure and temperature if you wanted to, but we don't need to. So if we look here, we have 1 atmosphere, and this is where it also gets important to write in your units. And we have 2 liters, because your units, yeah, in this problem, it may not seem as important, but you're basically saying what numbers go where. And so if you keep track of your units and you double check that the units are in the correct spots for the correct variable, then that will help you a whole lot. Okay. So if we rearrange this, P2 is equal to that times that, all divided by this guy right here. So we've got, because if we divide both sides by 200 liters, we get this. So now our units cancel out. We're left with atmospheres, which is good, and we can just do a little calculator work, right? And we can solve for that. So 1 times 2 is 2. Divided by 200 is 0.01 atmospheres, or 1/100th of an atmosphere. Okay, so that's how you solve a lot of these problems. Is you plug in your numbers, you work with your units, but be very careful because they oftentimes will give you these things in terms of Celsius. So let's do a similar problem, but with like Celsius before we do the other one. So if I said you have like 25 degrees Celsius, you've got 2.03 liters volume, and then it changes and it goes to 50 degrees Celsius. We want to know what our volume is going to be. So we can look at that, and we know that PV equals nRT, and so we're relating some temperature to volume here. That's what they're wanting us to do. So it's going to be V over T, right? V1, T1, V2, T2, because we can rearrange this and say, yeah, V over T is equal to N times R over P, is what we had talked about earlier. And it makes sense conceptually. Always double check, like, oh yeah, if I double the temperature, it should double the volume. That kind of makes sense. But we have to turn these into Kelvin. So 25 degrees Celsius is equal to, I think we have to add the 273 onto that. And that turns it into Kelvin, right? So if we do that, we get 298 degrees Kelvin. And then we also, if we did that with our 50 degrees Celsius, that's going to be 273 plus another 50, get 323 degrees Kelvin. So we need to be working with our degrees in Kelvin here, because if you look at this, we had 2.03 liters all over our first temperature, which was the 298 degrees Kelvin. And that was equal to this unknown volume, this V2, all over 323 degrees Kelvin. And if we rearrange that, we can say that V2 is going to be equal to this times, or this divided by that, times this right here on the top. You can see that because if we multiply both sides there, you would get Sorry, I just kind of wanted to give myself a little more space and that kind of messed it up. So if we look at this, we've got our multiplying both sides by, it's right there, and then your kelvins cancel out, you're left with just liters, and let's see what we get for our V2. So if we get 2.03 divided by 298 times 323, we get 2.20. I think if we look at the sig figs, I actually only gave two significant figures. So we can actually only write that out as 2.2 liters. And that would be our final answer. Because I only gave the two sig figs here and there. I gave 3 here, but it's limited. In any case, the volume has gone up, but not by very much. If you had originally used, this is incorrect. So I'm just going to put this as incorrect. But a really common mistake is for people to plug in the Celsius. And if you did that, you're going to get some numbers that are super bizarre. I think you would get like 4.06 because it's going to be times 2 effectively, right? So like the V2 would be 4.06 liters. But it is not, because we need to convert. So just be careful about that, okay? Also, so let's look at this one. This is more like your PV equals nRT. The ones that you might see more on, like, they typically have like one question like this on the AP test where you've got to relate these different things. And it's kind of like more of their freebie or easy ones. So just be aware about that. The first thing that I notice is that Celsius, that needs to be turned into Kelvin. That's going to be 283 degrees Kelvin. So they've given us the temperature. The R is always given because it's a constant. They've given us the number of moles, and then they have also given us the pressure. Okay, so we can plug them in as is. We could also rearrange. Either is fine. Let's just plug it in. We've got our 5 moles, and that's going to be multiplied by some R value. And then let's say we've got some temperature. So is that 283 degrees Kelvin and some R value. And then this is going to be equal to the volume times the pressure, which was 2 atmospheres. So we want the atmosphere liters 1, that conversion factor, which I believe I had right here. Atmosphere liters, yeah, it's the 0.08206. And that's the liters atmosphere mole Kelvin, I believe. I just want to double check that. 0.08206. Okay, so that looks pretty good. And now it's just a matter of kind of plugging in and solving for this stuff. We could also just cancel out some units. So we've got moles canceled out, our kelvins canceled out. And also, if you're canceling out your units here in the R, you're going to realize if you're working with Celsius. So that's another reason to write in your units, even when you're writing in your conversion factors, because I know a lot of people really want to just forget about that, right? So, and then also the atmospheres here will get canceled out with those atmospheres there. So we will be left with just liters. All right, so if we've got our 5 times 0.08206 times 283, okay? And then that is going to be divided by 2. That was the 58 point, what was that, 0, 5, 6, or 5, 7, 4, 5. What sig figs did I have? I limited us to one sig fig. Oh man. Yeah, I limited us to one sig fig on both those measurements. So this would have to be written out as the 60 um, liters for our volume here for this problem. So if you got kind of stuck there, I could have rewritten this out. Like I could have rearranged this. I'll just show you really quick over here, just to kind of demonstrate that this really is the same thing, but we'll just do it down here. So instead of having those numbers where they were written, I could have had my my 2 atmospheres down in the denominator right there. And I think this would have had to been the Kelvin. Because if you divide both sides by the 2 atmospheres, then it's over here, right? And so you've brought that now down here, and the atmospheres cancel out those atmospheres. These moles cancel out, the Kelvins cancel out, and you're left with just the liters. Okay, all right. Okay, so real world gases, they behave very close to ideal gas behavior, but it's slightly different. So there's 2 main things that you're correcting for. One is that molecules, they do interact with each other when they're gases. They're very weak interactions, but they do interact, and that molecules actually take up some space. So you can see that this is basically the formula PV equals nRT, but it's slightly different. You've got this stuff here, which is correcting to make things actually relate to reality, because the value that you're going to be plugging in here would be the observed pressure. Sorry, I'm going to try and make that red. So you've got this observed pressure that's being corrected by this A value. So pressure is going to be affected a little bit because we've got these molecules that are interacting. As molecules interact, the pressure that you observe is smaller than the pressure you would calculate for that number of moles. So this whole thing, you can imagine being equal to the, is what we would call the P corrected. So the P corrected is equal to this whole first piece right there. So A is going to allow you to correct from the amount that you observe, which is smaller than expected. So you can kind of see like, okay, well, this observed pressure is a little bit smaller because there's some A value in there. And so you can imagine if there's stronger interactions between molecules, they're going to hold on to each other and be kind of sticky, and they're not going to hit the outside quite as hard, right? And so that's going to end up causing the pressure to be smaller than you would expect if you were expecting things to not interact at all. And these A values, those are determined just through experiments, just observing what pressures you get with different molecules given the number of moles that you have, right? So there's also this thing right here where we've got our volume that's being corrected. And so you've got this V corrected. And the V corrected is equal to this V that you observe minus the B times N. And N here is the number of molecules. It's the same thing, same N that's on the other side of the equation. So basically what you have here is that all matter takes up some space, but we had been assuming that gases, the molecules themselves, don't take up space, and we're observing how much empty space they're taking up then in the container. So there was some space in the container, right? There's some mass that the molecules are actually taking up. So you've got this mass or this volume that's observed. That say you've got like a 1 liter container, and let's say like 1/10 of that liter. So let's just do some rough numbers. Let's say that you've got like a 1 liter container, and let's say 1/10 of that liter is being used up by the molecules. Then the corrected thing is going to be 0.9 liters. So the amount of volume that you actually have to work with in the container is being corrected by this B value. You can imagine that as you change your number of moles, that's also going to change their effect on the balance with the PV equals nRT. That's kind of why you're multiplying by n in both these situations. Don't worry too much about the math. The main thing here is just conceptual, that they want you to understand that gases, they don't always exactly follow the ideal gas law, and that's because they interact and they take up space. And that's all you really need to, like on the AP test, that's all they would expect you to be able to explain. And so gases typically are a little bit smaller, or sometimes a little bit bigger than what we would get from these gas laws. And it really depends also on the number of moles that are present. That throws off this calculation quite a bit. So be careful, because it's not always going to mean that the gas is smaller than you would expect. Sometimes gases are actually larger than you would expect. So just be careful. Yeah, that's the main idea, that you've got these corrected values that relates more to what you would expect with the ideal gas laws. Like you've got your P corrected and V corrected being actually related to the number of moles and temperature with the amount of pressure that's you're going to experience, observed, and the actual volume that's available to them / what's observed on that container. Okay, let's do a couple practice problems. So if I'm looking here, it looks like we've got some pressure, some temperature, and some other temperature. And so it looks like we've got some pressure, temperature, temperature. This looks like this is pressure 1, temperature 2. So if we think about our gas laws, we can relate pressure and temperature through P over T. Yep, that should work, because we've got pressure and then divided by temperature gives us equivalency of V equals NR. So that should work out for that. If you think about that, increasing temperature increases pressure. So that makes sense given those numbers that we're plugging in. So if we plug this in, it looks like 0.70 atmosphere over 299 Kelvin. That is going to be equal to 425 Kelvin. And then we're just solving for P2. And so you can plug that into your calculator and rearrange it. So we've got 0.70, 0.70 divided by 299, okay? And then times by 425 Kelvin. Okay, and so we've got an answer of 0.99, I think. Was it 0.99? Yeah, and I think it was 0.99498. But we can estimate that using our sig figs. We were only given 2, and we were multiplying, dividing, so it has to be 2. This is going to be 0.99 atmosphere. So that's our first answer for this first example. If we look at this next one, we're going to have some gas. It looks like we've got volume and some temperatures. So the first thing that I'm noticing, these are Celsius, so we gotta be careful about that. We gotta turn them into Kelvin. So 25 degrees Celsius is equal to the 273 plus 25, which is 298. And then this was, I think I actually did this math earlier. So the 50 degrees Celsius plus the 273 is equal to the 323 degrees Kelvin. And this is degrees Kelvin as well. Sorry, my K's are very messy looking there. And so if we look at this, PV equals nRT. This is V over T is equal to V over T. And it looks like we had a volume of 10 liters, and that is over our T1, which was the 25, just 298 degrees Kelvin. And that is equal to some V2, and this is 323 degrees Kelvin. And we should be able to solve for that. I think that's 10 divided by 298 times 323. And so, yeah, V2, this is equal to 10 point, what is that, 83, which we can estimate as, actually we can only give 2 sig figs, so this is only going to be 11 liters, right? So it's in liters, yeah, because the Kelvin's canceled out. Okay, so we got that. It did change the volume, but barely in a significant way. All right, and then I think if we look at this STP, this is standard temperature and pressure, which is going to be, I believe, room temperature, which is 25 degrees Celsius. Or let me just double check that. I'm pretty sure actually it's 0 degrees Celsius, isn't it? I was correct. It is actually at 0 degrees Celsius. My gut was like, okay, isn't this room temperature? No, standard temperature and pressure is 0 degrees Celsius. And it's also at 1 atmosphere. So it's at sea level. And so if we say that we're at STP and we've got about 50 liters of gas, that looks to me to be a little bit more than the standard volume of gas at STP. Because what basically this is saying is like PV equals nRT. When we're at STP, you know your pressure, and you know the temperature. And what you're basically saying is that this is 1. And then when you have this conversion factor, it's going to end up being the 22.4 liters. So if I end up plugging in not 1, if I get 50, it's going to be, I think it's about 2. It's like, I would estimate at around 2 moles is what I would do as a rough estimate. And then we can actually calculate this out. So if we have PV equals nRT, let's say that we have the 50 liters. So we have that, and we want to know the moles. So we know everything besides the amount of moles in this situation, because we're at the standard pressure, which is 1 atmosphere. They're giving us the 50 liters for our volume. And then we've got N, which is going to be multiplied by, I think it was 0.08206 liter atmospheres over mole kelvins. And then that was going to be times 0 degrees Celsius, which is 273 degrees Kelvin, right? So we need to actually go out and multiply these things out and see what we get. We could also just rearrange this a little bit. Probably a good idea. But I like to just write my math out like that just to see where everything is in the formula and the way I know it should be. And then I can double check it just a little bit easier. You know what I mean? So if we look at this, we have our kelvins, which get canceled there. We have our atmospheres getting canceled there. We have our liters getting canceled there. And we are left with, it's kind of weird. Oh, actually, I messed up. I totally messed up. Do you see where I messed up? I wrote the wrong numbers in the top and the bottom there. This should all be in the denominator, and this should be in the numerator. See, this is why you double check and have it written out in a way that you're familiar with. Because then you can be like, hold on, I multiplied or I divided something wrong there. So I've got my atmospheres there. It's also why you cancel out your units, right? Got units there. And then I've got moles in the denominator of the denominator. So that should work out. We should be able to solve for that. So if we have, it looks like 50 divided by 0.08206. Okay. And then we're dividing that by the 273. It looks like we're getting 2.23 mole. It looks like we're having to estimate it to, I mean, if I had written that as, it looks like that's written with one sig figs with just 50 there. So I would actually have to estimate this to the 2 mole because I only have one sig fig right there. So that's kind of the idea here. My estimate was actually right on the money. You can kind of see how this stuff works out a little bit with that example problem. I would encourage you also to just go through that with STP just to prove that 22.4 liters is equal to 1 mole, just to double check that skill that you're familiar with. So let's say you have a different problem. You've got your atmospheres, volume, temperature, and now we want to know the moles here, okay? So this is a thing where we have one situation and we're relating all these different things between that. So we've got pressure, looks like we have volume as well. Temperature, it's very cold. Wow. So I'm just looking at this. This is a very low temperature, very big container, very small number of moles. So I'm thinking because it's a small number of moles, it could be, or small atmosphere, it could be due to a small amount of moles, but it's also pretty low temp, so it's kind of hard to say. So we know that because that's constant, and we can solve for this. So you can rearrange initially, and you can say N is equal to PV equals RT. So you can rearrange at this point or later. It's the same math. You just gotta double check things a little bit. So if we plug in our numbers, we've got our pressure, 0.003. But see, now that I've written it this way, I've got to be careful with my units and make sure that units cancel out in a way that makes sense, which can be kind of hard sometimes with these. The volume was 500 liters. And then we have our R value, which was 0.08206. Yeah, I know that people really don't like canceling out units, especially when they get in denominators like this, but it is very, very useful in these types of problems. So we've got all of that in there. So we've got our atmospheres that get canceled out. We got our liters, which get canceled out. We want moles, and then Kelvin should get canceled out right here. So that was, what was that, 10 degrees Kelvin? That's very cold, man. It's very, very cold. Okay, so I believe that if we do that, that this Kelvin cancels out with that right there, and yet we're left with just moles. So this should solve for our final number here. 0.003 times 500. Okay. And then we're going to divide that by 0.08206. And then we're also going to divide that by 10. And so we've got 1.8 moles. It looks like we had 3. And this looks like we're limited by 1 sig fig again. So 1.827, but we're only limited to 1 significant figure. So we're going to have to estimate this as 2 moles of whatever this is. And you can always plug the number back into PV equals nRT and see if it makes sense. Though I know that people kind of don't want to do that math. If you know your exponent rules, you can just kind of double check that it's in the right ballpark, because I basically have like 10 up to the 3 and 10 up to the negative 3 being multiplied together here. So I know that my final answer for P times V should be around 1-ish. And then I know this is 10 up to the -1, -2, and 10 up to 1. Yeah, so you can kind of see like this is going to be 10 up to the -2 for my magnitudes. I'm just looking at like my raw magnitudes of power and seeing that this is 10 up to the second. This is 10 up to the, what is that? 1, 2, 3. S3. And this is 10 up to the 1, 2. And then this is 10 up to the 1, 2 for the R. And then the T is 10 up to the first power. And so you can kind of see roughly what you're working with, that this is 10 up to the -1 and 10 up to the -1 on both sides. So N should be like 10 up to the 0-ish power, which is around 1-ish. So this gives you an idea that helps you kind of ballpark these larger problems. If you're able to just kind of know roughly how your exponent rules work when you multiply large numbers, and you can think about these numbers in scientific notation. So I'll have a whole video on that as well. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.